And hi, I just want to start us off with binding energy. So before that, I want to make some notes. Okay, so um, in lecture 9, or rather rambling 9, because a lot of it was wrong, especially the Feynman diagrams. Um, yeah, I drew the Feynman diagrams to sort of have a neater way of visualizing the flow of particles, energy, momentum. It's especially useful to try and understand beta decay a little bit better. However, I drew them wrongly and I left the video up, partly out of convenience, partly because mistakes are the best teacher. So I just left them up because yeah, this is not my full-time job, okay? Yeah. So yeah, I left them up and I made corrections, and I typed out these corrections here, and I included all the citations over here, based on archive and all that. It's inside the nuclear physics directory under the ramblings here. Yeah, let me go to desktop. Yeah, under physics, you will be able to find the nuclear physics portion. This is the PDF you should open. You'll be able to find everything you need, plus citations, everything, including the YouTube video I was referencing the last time. I think I kind of missed out on the Cambridge one, but okay, you have all you need here. I'm not going to overload you with too many things. So pardon that I didn't put the Cambridge reference just yet, but this is pretty much all you need to really understand Feynman diagrams a bit more. But for my purposes, I was just using them as a neater way to represent particle flow, energy flow, how the particles, momentum, energy, and charge are being transferred from one thing to another. Okay, it may be too detailed, okay, for general understanding of nuclear physics. So just know that they exist. Know that this is what real physicists use. Okay, I made mistakes in the past ones and I made corrections in a follow-up video. And yeah, this is it. I left this online for the reasons explained before. But now I want to get on to binding energy. Binding energy, which is a bit more, I'm more confident of it because I actually learned it rather than the Feynman diagrams. Yeah, and I got my exams, I got good grades and all that, whatever. Okay, I know my stuff here now. Feynman diagrams not so much. Okay, so pardon me on that. Yeah, let's get started with binding energy. Okay, I'm gonna close this and let's open Ocular. I'm gonna get lecture 10 to 20. Okay, it's almost 2.5 minutes in, or more than that. So, let me switch on my annotations and let's do lecture 10, binding energy. Okay, I think in previous lectures, I kind of likened that energy is released when, there's an attractive force between two bodies, let's say an asteroid and let's say planet Earth. Okay, this thing is away from planet Earth and there's attractive force that's coming called gravity. Okay, when you let gravity take its toll and the asteroid crashes into Earth, there will be lots of energy released in the form of an explosion. Okay, so there's a lot of heat and other energy released. Okay, the same thing can be thought of for uh, the strong nuclear force. So here we have a proton, here we maybe, yeah, here we have a neutron, here we have a proton. Okay, there is a strong nuclear force between them if you have, and this thing will combine together and become a deuteron. Okay, deuteron. Why deuteron? Deut means two, and yeah, deuteron is basically the nucleus for deuterium. Okay, deuterium. Okay, let me draw the X diagram. Okay, deuterium is what we call this is the electron, yeah, electron. This is the diagram. Dot cross diagram we use in chemistry a lot, so I'm using that to denote electrons. So deuterium is what makes up what makes up how do you call? It's a heavy hydrogen. It makes up heavy water. Okay, so heavy water, you will hear this often in nuclear reactor engineering because D2O. Heavy water. So deuterium's like that. Okay. So what happens when these two proton and neutron combine? Proton and neutron, proton plus neutron. So which one was? I just want to make sure it's consistent. Proton, neutron becomes deuterium. And remember, there's a lot of energy that's being released because there's an attractive force between these two particles. Okay, these two fermions, uh, yeah, fermions. But okay, let's put the particle naming aside. Okay, these two particles have attractive force between them. You let them go, they crash into each other and they will release energy. Okay, the energy can be in form of kinetic energy, but usually after a while, you let it radiate out of the nucleus, it will become a gamma ray. Okay, so this is what we call N gamma reaction, and because we introduce a neutron in, and then a gamma ray comes out. Okay, so this is what I call N gamma reaction, neutron capture. Okay, so where is this binding energy? Okay, this binding energy was released in the form of this gamma photon. Okay, so in order to split up this, deuterium nucleus into the neutron and proton, you need to supply energy to separate them. Okay, so that's the binding energy that we are talking about here. Okay, the useful way to measure how much binding energy there is to have this thing called, we use this thing called mass defect. Okay, mass defect. Okay, and this is not to be confused with this thing called mass excess, because there are two of these mass terms used. Okay, online you may see this mass excess and mass defect. Okay, they are different. Okay, they are different. I want to make it clear they are different, but they describe more or less the same thing. Okay, mass defect is not mass excess, but they describe similar things. Okay, or rather they are both used, to calculate binding energy. So again, just to introduce you to these concepts, binding energy is the energy you need to supply to split apart your nucleus. In this case, it's this deuterium, the proton and neutron. You need to split it up back into its constituent the proton and neutron. You split up the deuterium into its protons and neutrons. Okay, so let's just do a simple exercise. We have lithium-7. Okay, lithium-7 has 7 particles, as the number implies. Okay, lithium itself has 3 protons. 3 protons, 4 neutrons. 1, 2, 3, 4. Okay, let's just hypothetically combine them together. Okay, then you have lithium-7. Okay, I'm probably not going to draw it correctly. So this is a lithium-7 nucleus. Lithium, you identify it by the number of protons it has. Lithium always has 3 protons. Okay, 7 is the total number of particles in the whole nucleus. In this case, 7. Okay, so you have this all of this together, you will release binding energy. You will release binding energy. Okay, so of course, the more nucleons, the more protons and neutrons you add, the more binding energy is released, because it keeps, there's this dynamic of you letting the particles crash together when there's a strong attractive force between them. Now, if you notice, these protons are together in the nucleus even though they are positively charged. Okay, positively charged particles repel each other normally. all right? And they repel each other normally. But the nuclear force is so strong that they still keep together. So that's how strong the nuclear force is. Very, very strong. You can refer to some of the other notes, but to see how strong this nuclear force is, okay? But nuclear force is strong, this strong nuclear force is very strong, as the name implies, and it's a very short range force. Okay, so this is the basics of binding energy. But by itself, is it really useful? Okay, we don't we are usually not as interested in binding energy by itself, not all the time. Okay, but we are more in physics. We like to, or rather nuclear physics. We use binding energy, of course, to find out how much energy is released in a reaction, or rather, we use it to calculate how much energy is released in a reaction. Um, yeah, but that's not exactly so useful. Okay, so let me show you what is binding energy useful for. Useful for. Conceptually speaking, okay? Conceptually speaking, conceptually speaking, okay, binding energy, I just call it BE for short now. Binding energy is useful. All right, useful to describe how tightly a nucleus is bound. Okay, well, not binding energy specifically, it's binding energy per nucleon. Okay, this is a very important metric. Okay, so conceptually speaking, binding energy per nucleon is used to describe how tightly a nucleus is bound. Now, of course, like I said here, the more nucleons, the more protons and neutrons you put together, the more binding energy is released. That is obvious, okay, because there's attractive force between them. However, the attractive force between each particle is not equal, so to speak. Okay, some particles may be more tightly bound, okay, than the other. How do you measure how tightly bound particles are? You take the binding energy and you divide by the number of nucleons. So what you will do for lithium-7, okay, you take this total binding energy. Okay, example, okay, how to calc. You take this lithium 7, okay, you have 7 particles. Okay, this lithium-7 nucleus, okay, how do you so-called calculate this? How do you calculate the binding energy per nucleon? Okay, so you compare, okay, so you have hypothetically 7 particles, 3 protons and neutrons. You combine it together. You take the energy released, usually as a form of a gamma or something else, but usually it's gammas. Okay. Yeah, I'm not saying this reaction will happen in real life because usually it does not happen like that. It will happen sequentially. Okay, but anyway, just for the sake of explanation, pretend this happens. Okay. So a lot of the energy gets released. Okay, the energy is released. And what do? You take this energy and you divide by 7. And that's how you calculate binding energy per nucleon. Okay, so I mentioned just now, you can't actually have all these 7 particles sort of come together magically in one step, and then you just try and measure all how much energy is released as photons. This just doesn't happen. So you can't measure binding energy like that. How then can you measure binding energy? Oh, this is a BE. Yeah. How to measure binding energy? So binding energy, we can use E equals mc squared. Okay, let me put the M naught there. That means rest mass, but just for the sake of those who don't know relativity, just take that it's your mass. Okay. Okay, E equals mc squared. Why is this useful here? Since you cannot measure all the gammas coming out directly, we can use something else. We can actually weigh the individual protons and neutrons, and we can weigh the we can weigh the lithium-7 nucleus. Okay, so let me draw weighing scales here. Okay, so your lithium-7 is going to be, I'm going to draw this. It's going to be lighter than the 3 protons plus 4 neutrons. Okay, I'm going to put the weighing scale here. Okay, we call this, okay, so why is the 3 protons and 4 neutrons heavier than the lithium-7? Because when you release the binding energy out, you actually lose some of the mass. Okay, there's so much energy out that you can actually measure this mass loss. Okay, since the energy was lost as gamma photons, this whole system actually lost mass. Okay, so that's why we call this mass defect. Okay, reaction, and we call this mass defect. Okay, why is it called mass defect? It is a defect relative to protons and neutrons. Okay, relative to protons and neutrons, there is a mass defect. So this is what we use to so-called calculate the binding energy per nucleon. Or rather, we calculate the binding energy first. So we take the masses of 3 protons and 4 neutrons. Okay, they have been measured experimentally, and then we can measure that, we can compare that to lithium-7. Okay, so this is what we are doing here, and this is what this equation there is doing. There's an exercise for you there. You can go and do the math, but basically that's the concept behind the math. Now, if you were to plot it out, as you see here, so I want to again say some particles are not bound as tightly as others. So the deuteron here, hydrogen 2, as you can see, this is not very tightly bound. Okay, some particles are more tightly bound than the others, partly because of the charge that's going on, partly because of other quantum mechanics effects. Okay, I'm not going to explain all of that, but what is useful is that just know not all particles are bound equal. Okay, there is this binding energy per nucleon curve plotted against the mass number. Okay, plotted against mass number. This is your number 1 curve when you want to used to explain the physics, or rather why nuclear reactions can release energy. Okay, why is there fission in one way and fusion in the other? So as you can see here, uranium-235 and uranium-238 has a lower binding energy per nucleon than, let's say, iron-56 and some other elements here. So if you split up these uranium atoms, you're going to, or this uranium nuclei, you're going to get energy. Okay, if you split them up and you arrive here, if you try splitting them up into the hydrogens and stuff, you're going to lose energy. Okay, so the splitting must result in all these particles, or rather nuclei in the center. It can be strontium, can be krypton, iron, so on and so forth. Likewise, over here, when you have hydrogen, isotopes of hydrogen, for example, this what we call tritium, because it's 3. Okay, tritium is radioactive, by the way. Tritium and deuterium usually try to combine them to form helium, and then 1 neutron will come out. Okay, you will have energy release because the binding energy per nucleon for helium is much higher um, than for tritium and deuterium. Okay, you'll have to do the math to convince yourself of that, but that's basically how it works. So, I mean, yeah, just know that the fundamental thing for binding for nuclear physics, why there is such why some reactions release energy, some reactions take energy, why fusion is good for light elements to release energy. I mean, fusing light elements will release energy. Splitting heavy elements such as uranium will release energy, is because of this binding energy per nucleon curve. Okay, that will try to explain things. So a lot of these things uh, they have to do with addition, subtraction, and then you just multiply by the c square. Okay, so you have to do some math, but the math here is relatively simple. Okay, the math here is relatively simple. Okay, so that forms your fundamental baseline for why you can get energy from recombining different combinations of protons and neutrons. Okay, so yeah, one more thing is I want to sort of clear up confusion in case you read of it before. Potential confusion. Okay, mass excess versus mass defect. Okay, so mass defect versus mass excess. So mass defect we already explained before. Okay, mass defect we explained before. We take the mass of this lithium-7 and we compare with, okay, we compare this with the mass of the 3 protons and 4 neutrons. Compare mass compare with 3 protons and 4 neutrons. This is mass defect. Okay, so what's mass excess? Let me write this in orange. Mass excess is, let's say, your lithium-7 again. What do you compare with? You have a mass comparison with, okay, just get this straight. 1/12 mass of carbon-12. Okay, 1/12 the mass of carbon-12. Why carbon-12? Okay, okay, carbon-12 is the standard nuclei or standard nuclei used to measure with which all other particles are weighed against. Okay, this one, 1/12 the mass of carbon-12 is what we call the atomic mass units. Okay, 1/12 the mass of carbon-12 is what we call these atomic mass units. So I will probably want to revisit this, but just know that the mass of one neutron and mass of one proton, they are not the same, and they usually like to use atomic mass units, AMU, to measure them. Okay, if you ever see a mass of proton being 1.008 or 7 or something like that, I can't remember which is which off the top of my head, I don't have the figures, but these are in atomic mass units. The definition for atomic mass units is 1/12 the mass of carbon-12. Okay, there's a so most of the time this 1/12 the mass of carbon-12, that is the standard mass that you use to measure everything with. Okay, so this is what you're using. Okay, the better way to think about it is that, okay, You want, hmm. Okay, okay, never mind. I will leave it as this. Okay, I will leave it as this. This is the definition, so you get a concepts right. Most of the time, uh, if you want to calculate mass excess, you will just take the practical way, practical way of mass excess. Okay, and you'll be still correct. Okay, you'll be still correct. Is to take the mass of lithium for, let's say, lithium 7. Okay, for lithium 7. Practical way of calculating mass excess for lithium 7. You take mass of lithium 7 and then you minus 7.0. Okay, that's it. Yeah, you minus the number here, or you find the difference between the numbers. Whether it's a plus or minus, whether it's this or this, again, I have to go and check because I didn't have my notes prepared. But yeah, you just have the difference between these two. You will have your mass excess. Okay, so you're comparing mass of lithium 7 against 112 the mass of carbon 12. Okay. All right. Okay. Times 112 the mass of carbon 12, and then you have to times the number of nucleons. Okay. I think that's the more correct way to put it. Yeah, but I just need you to know this is a comparison with 112 the mass of carbon 12 times the number of nucleons. Okay. Okay, I think that's enough. I will stop here. I don't want to keep rambling on, but yeah, we talk about binding energy. We talk about mass excess, mass defect, mass excess. Okay, and why binding energy is useful. Gonna stop, and I'll see you guys next time.